Assalamu alaikum. In today's video we would be discussing about auxiliary properties. So what exactly are auxiliary properties? When we are defining a system, we mainly indicate the atomic species we would be using and the atomic positions, but besides these two properties we can also add some other information, and those additional information are termed as auxiliary properties. So there are some limitations in case of using auxiliary properties, that is, not all file formats support all kinds of auxiliary properties. For example, the XSF file only supports the forces of atoms. The LMP file format, which we would be using for our LAMP simulations, only supports ID type, electric charges and velocities. And finally, the CFG file format supports most of the properties. There are mainly two kinds of auxiliary properties. Firstly, per atom properties, and secondly, system-wide properties. So per atom properties are when we define the property of each atom or a particular atom, we call it per atom properties, and when we define the property of a group of atoms or a system of atoms, we call it the system-wide properties. Here is a list of per atom properties. Firstly, displacement vectors. So how we would be using it is, firstly we create a .text file. In that text file we would be saving our properties. Then when we are calling the ATOMSK, we would be calling that properties text file, and we would be creating our structure. So here you see displacement vectors. In a text file we would be firstly using the keyword displacement, then the ID type and the displacement along the three axes. In the third bracket you would see that the displacement sx1, sy1 and sz1 is given. So the ux, uy and the uz are the atomic displacements along the three axes, and the sx1 mainly indicates the displacement of the shells. If your displacement are not particularly numerical values and is in the format of a function, you can also use displacement functions keyword, and here ux equals to a function, and you can use all these functions along with the operators plus, minus, multiplication, division, etc. Then if you want to define the atomic velocities, you can use the keyword velocity, the ID type and the velocity components along the three axes. If you want to define the ionic charges, you can use the keyword charge, the atomic species. The capital Q1 indicates the charge of the atom, and the small q1 indicates the charge of the shell. If you want to define the atomic type, so you can use the keyword type, the species of atoms and the type you are assigning it to. Apart from these properties, if you want to define your own arbitrary property, you can create that also. Firstly, you have to use the keyword auxiliary, then you can use the name of your property. You can use any name of your property. Then you have to assign a particular numerical value to a particular type, atom type. So these numerical values you can obtain it from experimental setups or from simulations. Firstly, in case of system-wide properties, you can see the supercell parameters. Here you are creating a system of atoms mainly from a group of atoms. So what you need to do is, if you think of a supercell, you need to define the coordinates of all the endpoints. So this is what is given here. In case of a plane, we can see that it is a 3×3 matrix where the coordinates are given, and you can also show it by the conventional system, that is by the length and the angles. Next you can see the current crystal orientation. So you can use the word orientation, and you can identify or indicate the Miller indices along the three axes. So what you need to know here is that in current crystal orientation, the orientation of the crystal does not get rotated, but what happens is the new crystal orientation gets defined. So for example, your current crystal is now along the x-axis. So after you use the word orientation and you give your auxiliary property here, and in the orientation you give that your x-axis is along the 60 degree with the x-axis. So it will not rotate your system, it will define that 60 degree is the new x-axis. This is how it works. Then comes elastic or stiffness tensor. So in case of elastic materials, when you apply strain, when you apply stress, a particular amount of strain or the element or material is deformed in a constant rate. So that constant, proportionality constant, is here defined as elastic or stiffness tensor. So according to the formula, you know that stress is proportional to strain, and in the proportionality constant, you know that stress equals to a proportionality constant into strain. And if you can define this proportionality constant as a 6 into 6 matrix, you can this is termed as elastic or stiffness tensor. In case of orthotropic materials, what is orthotropic material? An orthotropic material is a material where the property is unique along all the axes. So in case of an orthotropic material, instead of 6 into 6 matrix, you can define this system with a 3 into 3 matrix, that is 9 elements. And the compliance tensor is the exact inverse of elastic or stiffness tensor. As you can see from the equation here, strain equals to a proportionality constant into stress, and this proportionality constant is compliance tensor. And you can also use the compliance void in case of orthotropic material. Now there are some examples. Firstly, how we can use ionic charge. So here you can see a charge.txt. So in a text file, we can use the keyword charge, then the element type sodium, and the charge value 1.0. So after saving this, we can create a rock salt type of lattice with a lattice parameter 5.64, sodium and chlorine, and we can call the properties in the text file, and we can use the output CFG for visualization. In the same way, you can define your own custom properties. Auxiliary, my energy, you can use any other variable name as you wish. Here are the atom ID types and some values assigned to that particular atoms. Here also we can see that after calling the properties energies.txt file, we can define our custom properties. Here are the system-wide properties examples. So this is an example of creating a supercell where we are creating a 3 into 3 matrix and then calling this 3 into 3 matrix as a format of text file and then saving it. And finally, delete properties. So if you want to delete a particular property, you can use remove property q. So this q indicates the atomic charge. So if you want to delete only ionic charge, you can use remove properties ionic charge, and that is q. And if you want to delete all the properties, all the auxiliary properties, you can use remove property all to delete all the auxiliary properties. So now I would be going through some demonstration. So I would be opening the terminal. As you can see, in a charge.txt file, I have already created the keyword charge, element type sodium, charge 1.0, element type chlorine, charge -1.0. Now we can create our structure. So our structure is ATOMSK, create rock salt lattice parameter 5.64, sodium, chlorine, properties charge.txt, file format CFG. So our structure is created. Now if we want to visualize it, you can see this is our sodium chloride structure. The small spheres, green spheres, are our charges. Now we can try out the custom properties. So here you can see in the energies.txt file, I have used auxiliary my energy. So you can use any other name here, and we are in this ID type, we are assigning a value of -2.3, -20.3. So you can use your own values here. Now ATOMSK, create rock salt lattice parameter 5.64, sodium, chlorine, duplicate 222, Now calling the properties energies dot txt file and saving it in CFG. So we want to overwrite our previous system. Now if you want to visualize it, you see our system is duplicated and the small spheres you see are our charges. So you can also color it as you wish. So in case you want to color it, so I will show this in the later videos about Ovito, how you can use color coding according to your wish. And finally we can use the supercell. So for this supercell we have already created a new box.txt where our auxiliary keyword is supercell, and we are forming a 3x3 matrix there, and these are our lattice parameters. So if we use the code, ATOMSK, firstly we call nacl.cfg, then properties new box.txt, and we save it in tetragonal.cfg. So our file is saved. Now for the visualization, here you see that there is no simulation box. What it means is that now this group of atoms is a particular system, and you can define the properties of this particular system as you wish. So this is all for today's video. Thank you.